Okay, I'm going to begin section 6.1 now. In chapter 6, we're just going to cover 6.1, 6.3, and then 6.4. The main topic here in the chapter is systems of linear equations. A system of equations is where you have one or more equations and one or more unknowns. So I've got some examples of some systems. Here would be two equations with two unknowns. The unknowns are x and y. Okay, usually we have like a bracket to enclose all the equations together in a group. You'd see that in a lot of books. Now, the solution to the system would be all the values that are solutions to each equation. All right, so if I were to just kind of play around with the numbers here and maybe try x equal 1 and y equal 3, like that would make a true statement with the first equation, right? Because if x is 1 and y is 3, 2 plus 3 is 5. But if x is 1 and y is 3, in the second equation you'd be saying negative 1 plus 9 is negative 6. That's not true. All right, so x equal 1, y equal 3 would not be the solution to the system. If you were to kind of play around with the numbers more and try x equal 3 and y equal negative 1, then if x is 3 and y is negative 1, you're going to have 6 minus 1 is 5, that's true, and then negative 3 minus 3 is negative 6, that's also true. All right, so x equal 3, y equal negative 1 would be the solution to the system. All right? You can write your answer either as an ordered pair. I'll comment more on this shortly when we talk about the graphing method, but you can use an ordered pair that is point notation, or you can just simply write x equals whatever number it is, y equals whatever number it is. Okay, either way is fine. Now, obviously, we don't want to be guessing and checking. Like, we want to be, using some sophisticated methods here for solving. But I'm just using guessing and checking at the moment just to get the idea across of what a solution is. Here's some other examples of some systems. So here I've got two equations with two unknowns. Now, we call this a nonlinear system. Your book has a few examples of nonlinear systems, but we're not going to work through any of those types. In other words, you're not going to have to worry about like powers of x, or like a 1 over x, or like a e to the x, or ln of x. Those are not linear equations, and our focus here is going to be on systems of linear equations. Okay. Here's another example. In this one, I've got three equations with three unknowns. The three unknowns are x, y, and z. And now the idea would still be the same, find x, y, and z such that all three of these equations are true simultaneously. Okay. Now the number of equations doesn't always have to match the number of unknowns. Like in this one, I've got two equations, but there's three unknowns. And again, the idea would be find x, y, and z such that both equations would be satisfied simultaneously. If a system has no solutions, it's called inconsistent. We'll see some examples of that. If a system can have infinitely many solutions, it's called dependent. We'll see that also. And otherwise, if a system has only one solution, then we call that an independent system. So like up here, this system would be an independent system. There's only one solution. That is when x is 3 and y is negative 1. In this section, there are three methods mentioned for solving a system. We'll actually look at a fourth method for solving a system in a later section here. So one method that we can use is called the graphing method. Okay, now we're working with linear equations, so we're working with lines. And in the graphing method, you're going to graph the lines, and your answer will be the intersection point where the lines meet there. Okay, so let's take a look at some examples. In this first one here, I've got a system of two equations and two unknowns. Now, in these equations, I've rewritten both of them so that they're in the form y equal mx plus b. That way I can, graph each one of these lines by working off of the slope and the y-intercept. Same system, right? This is the same as what I originally had. I've just solved for y on each one. There's no problem with doing that. So the first line has a slope of 1 and a y-intercept at -5. Okay, so here's 0, -5, which I can use as a start point, and then work off of the slope. The slope is 1, so I'm going up 1 and to the right 1. And you can do that several times to gather up a bunch of points on this first line. That line would pass through the x-axis at the point 5, 0. And so there I've drawn that first line. Now the second line has a slope of -2 and a y-intercept at 1. So here's 0, 1 on the graph, and then if I work off of the slope, I'm going up 2 and to the left 1, since that's a negative. Go up 2 to the left 1, or you can go down 2 and the right 1, same thing. Okay, do that a couple of times and gather up some points on this line, and then draw on that second line. Now my answer is where the lines intersect. So if you're using the graphing method, like any other graph that you make, it's important that you be neat with the graph. You don't want to quick slop up something and then you got to eye down where the lines meet. That kind of defeats the purpose of using this method. So be neat, like you would any other graph. And in this graph, it looks like the lines meet at the point 2, -3. Okay, so I think x is 2 and y is -3 would be the solution. Now, of course, I'll want to check that. So if I plug those numbers into my system, I should get a true statement there on both equations. So let me check that now. X is 2 and y is -3. Is it true that 2 minus -3 is 5? Yeah, 2 plus 3 is 5. And is it also true that 4 minus 3 is 1? Yes. Okay, so both equations are satisfied, which means that x equal 2, y equal -3 would be the answer. You could also give the answer as a point, using point notation. And of course, pay attention to how My Math Lab wants the answers written. They'll tell you the form that they'll want it in. Here's another example. Okay, and you have 2 lines. Okay, and you want to see where the lines intersect. So I've rewritten the top equation here into the form y equal mx plus b. The bottom equation is already in that form, right? So if I were to graph y equal -3/5 x plus 3, the y-intercept is at 3, so here's 0, 3. I can use as a start point and then work off of the slope. The slope is -3/5, so I'm going up 3 into the left 5. And I can draw on that line then, passing through those 2 points. Here's my other line, y equal -4/5 x plus 2. Has a y-intercept at 0, 2, and then can work off of the slope. Slope is -4/5, so you're going to go up 4 and to the left 5. Okay, well, and then draw that line. So both of these lines are going to intersect at the point -5, 6, and so I think x is -5 and y is 6. If I quick check that, let's see, is it true that -20 plus 30 is 10? Yes. And in the other equation, if x is -5, the 5's will cancel there. -3 times, so you'd have -3 times -1 is 3. 3 plus 3 is 6, and that's my y value. So both equations are going to produce true statements there. Okay, here's another one. Solve the system. Okay, again, I've rewritten each one of these equations into slope-intercept form, y equal mx plus b. So with this first line here, the slope is -2 and the y-intercept is at -1. Here's 0, -1 I can use as a start point, and then I'm going up 2 into the left 1, up 2 into the left 1, or you can go down 2 into the right 1, same thing. And then in this other line, which ends up being y equal -2x plus 4 in a slope-intercept form, 0, 4 is my y-intercept, and I've also got a slope of -2, so I can go up 2 into the left 1, or here you go. If you go down 2 into the right 1 twice, that line should pass through the point 2, 0 on the x-axis. Okay, and then draw on that second line there. Now my answer is where the lines intersect. Now these lines are parallel lines. How I know that is because parallel lines have the same slope. Parallel lines, of course, will never intersect. And so because these lines will never intersect, this system is going to have no solutions to it. A system that has no solutions to it is called inconsistent. And in your answer, you can just write the word inconsistent, or the empty set here is another symbolic way to represent a system that has no solutions. Or you could also write no solutions, since all three of those items mean the same thing. Okay, here's another example. I want to solve the system. So if I rewrite the top equation into slope-intercept form, add 2x to both sides, I get y equal 2x plus 4. In the bottom equation, if I divide by 2 on both sides, I'll have y equal 2x plus 4. Okay, so I'm going to draw that first line here, y equal 2x plus 4. Here's 0, 4. I'll use that as a start point and work off the slope. The slope is 2, and so I'm going up 2 into the right 1. Okay, or you could go down 2 in the left 1. If you do that twice, this line will pass through the x-axis at negative 2, 0. And you can draw on that first line there. And the second line is y equal 2x plus 4. Okay, so I'll draw that line, and what I'm looking at then would be a line on top of itself. Now, my answer is going to be where the lines intersect. Well, if I've just drawn the same line twice, then those lines are going to intersect infinitely often, right? So there's going to be infinitely many solutions to this system, or you're going to have what's called a dependent system then. When you give your answer to a dependent system, we usually do that using an ordered pair notation. So I'm going to write down a point, x, y. It's just I want everything to be either in terms of x or everything to be in terms of y. Well, I know what y is in terms of x, right? Y is 2x plus 4. So in the y coordinate spot, I can just write 2x plus 4. And this point here would be my answer. Okay, now this would be one way that you could describe to somebody that there's infinitely many solutions. If you give me any x value, and of course there's infinitely many numbers that you could give me, I can always find a y value by taking 2 times that number plus 4. So I would be able to gather up infinitely many points on this line, which is going to be the same line drawn twice. But the point is that you can start the problem by giving me infinitely many values for x, any number that you want. Okay. Now, solving a system by using the graphing method does have a major drawback, and that is that we're not going to accurately be able to determine the coordinates of a solution of an independent system in some cases. So here's an example. Okay, if I have this system here and I want to solve it using the graphing method, I'm not sure that that'd be a great option, because the solution to this system would be x equal 35/8 and then y equal 11/4. So if you were to use the graphing method, do you think that would be a point that would be easy for somebody to see on a graph? I think probably not. Usually with the graphing method, we like nice counting number values for x and y. Neither of these were nasty numbers here. Okay, but if you get like oddball fractions or decimals or things like that, the graphing method to me is not really a suitable option. Okay, in other words, that point would be very difficult for somebody to see on a graph. All right, so therefore it's necessary to know some other techniques rather than just the graphing method. And we'll stop there.